recorded and they are going to be posted right after the class. And hopefully the sound quality also should be fine. Okay, now, the first thing that today we're going to start is, but any questions so far? If you have any questions from the previous contents that we had, no, you feel energized? You feel energized without the question, huh? Yes? Now, guys, today we are going to explore one of the very most interesting part of the calculus and part of the math. And you may ask yourself, why I say this is a very interesting concept? Because I say that in most of the modeling problems that you use math, you are going to see this number. Natural number or Euler's number. But how much is that if you remember from the advanced functions? 2.71. I normally forget that numerical value because I never use that numerical value. I always work with the E. Now, if you remember from your advanced function, there is a, I'm going to talk for 3 hours about the beauties of the number E, then I start the lesson today. But before I start, I'm just going to tell you the natural number that you saw in your advanced function comes with a very interesting definition. And that definition, now that you have learned the concepts of the limit, you can just say, okay, what can I use? The prior things that you learned in the calculus course to define E. And I'm going to say that to you, don't search further, because the definition of E is this. If you take the limit of this expression when n goes to infinity, you can see that, for example, you could just put n equal to 1, then at the very starting of your trend, you get the value of the natural number. Please, yes, you have a question. I'm so glad that you have a question. No. Say what? Yeah, please. Now, please write this definition, because we are just going to use this definition along the way today to prove something. Now, but why I say that the natural number is so beautiful? One of the first reasons is that there are 2 reasons today, and 2 of them you are just going to learn way in the higher years when you just go for the math. One of the main reasons is that we say that if you have a natural number, and this is called e to the power of the x, we say that this function is a little bit, I should say, too bizarre. Because when you come to talk about its instantaneous changes, you remember from the things that you learned a couple of weeks ago, we said that if we have a function, f of x, and in the calculus and real life, you are not just looking at static pictures, you are looking at the movie. All the things around us, they are changing somehow. Then all the things that you learn from the advanced function course is not going to be relevant when you just want to mirror them to the real life. Then that was the reason we said that we defined this operator to say that the changes of the function f of x, when a variable of that function changes, is given by this formula. We said that the limit of f of x plus h minus f of x over h when h goes to 0. Do you remember that, huh? And we just worked with this for a couple of days. However, we saw that, for example, if we have x to the power of 10, its rate of change with respect to the x becomes 10 times x to the power of 9. Now, but when we work with this function, which is the natural function, or sometimes they call that the Euler function, if you add I, we're not going to talk about it now, you see that the changes of this function with respect to the x, look at this, I'll emphasize here, if you have x here, you have x there. You see that the rate of changes of this function, then this function starts to be dynamic with respect to the x. If you put this in the formula, you see that it gives you the same thing. And that's why this function is very interesting. It changes, but the rate of changes that it has, it's the same as the function itself. And that's one of the things that we are going to say, okay, that function is a very interesting thing for us. The other reason we are going to talk about that a little, maybe today, and maybe more in the next session, is that normally scientists just come to work with this function a lot. And they say that, okay, for example, e to the power of x plus e to the power minus x. For example, e to the power of the apple plus e to the power minus apple divided by 2, it gives you another function, which they call that hyperbolic function. Cosinus hyperbolic function. We are going to see some of the examples at the end of these handouts that we have. Section C, there are 3 or 4 questions which requires you to work with this hyperbolic function. Can you see that some scientists, they are really obsessed with these numbers. They mix them together and they find very interesting things. The last anybody can see if I write something there? Tony? Everyone can see that? Everyone is fine? Everyone is fine? Okay. The last thing which we really are going to talk about this, you're going to see this more in future, is that this function, and also you have one question at the end of handout. And they say that e to the power x is going to be represented by infinite number of the terms, which is going to be this. Let me just not to write the sigma form, which is going to be a little bit confusing. And also you have something very similar to this at the end of this handout, and they say that, for example, e to the power of whatever function it is, it's the sum of infinite terms, which it shows that it is my sigma. It's a little bit odd looking compared to a normal sigma, but that's the sigma. Means the sum of infinite terms of x to the power n over n factorial. And that's what they call that. You do not need to prove it now. You do it in the university. That they call that Taylor or Maclaurin series. You do not have it these days. But there is something at the end of this handout. Then you see that these numbers, for these kind of reasons, e to the power of the x, you're going to love this function a lot, because they are like the bread, which is always an indispensable part of your breakfast. Whatever you want to do, you always have bread. In math, most of the things that you do, you're just working with the e to the power of the x. Now, the question now we are just going to work is this: how to prove and why the rate of change of e to the power of the x is the same function. Maybe you think that probably I haven't had my coffee in the morning, and that's why I talk about something which is odd, but I'm going to prove it to you why it's going to be like that. Now, I'm just going to use this definition here, but instead for f of x, but before I continue, any questions so far? Any questions? Everybody, because of these 3 reasons, of many reasons which I counted today, are you in love with this function? You love this function, everyone? Oh, I'm so glad. I can see everyone is really interested in this function. Now, the thing is that how to prove the change of the function is the same as the function itself. Now that's what we plan to do. We say that d over dx of the function, which is e to the power of x, is going to be what? The structure is given. And the structure is, we say that the limit of, I say that f of x plus h. F of x is x e to the power of the x. Then it becomes e to the power of x plus h. It means that wherever I see x from the function, I take this away and I plug in x plus h. Then as a result, this is going to be the first term. Minus f of x, it's going to be e to the power of the x over h. H going to be 0. I haven't done anything yet except I plug the function into the structure that is given. Now, in order to proceed, I'm going to do something. I say, look at these two terms. Look at these two first terms which I have. For both of them, I see that there is e to the power of the x, which is term which is common between them. And I also know from this identity in the math that e to the power, not e, any numbers, a to the power n times m is essentially a to the power n multiplied to the a to the power n. That's the thing which you have also on the first page of your notes.
N plus m.
Thank you. It means that honestly, I had to have my first copy today before showing up in class. Now, you see that e to the power x plus h, that if you look at that formula, it means that it can be written as e to the power x times e to the power h. Correct? Now, that's what I'm going to do. Then I say, I take e to the power x, take this out from this term, but let me write all of it. It becomes limit of e to the power x times e to the power h minus e to the power x over h. H goes to 0. Correct? Now, I see that I have two terms e to the power x, which they are exactly the common factors between them. Then you may say that, okay, I'm just going to factor this, and I take this out from the limit. Why I can do that? I'm just going to write it like this. My other color. There it is. Okay, now you see that I have a to the power of the x. I factor this out. I'm gonna write it like there, and I say, okay, e to the power of the x, which is essentially that term, is taken as a common factor. I factor this, G. Then I say, okay, I'm gonna write. Let me write it this way. The limit of e to the power x, then I have here, I have e to the power h minus 1 over h. H goes to 0. Okay, now, guys, look at this. This part, please, everyone, pay attention to this part. In this part, you see that you're gonna learn something interesting. Look at this. if I have e to the power of the x, which is a common factor to both these terms, I took this out, and I see that the limit is emphasized on h, and it says that the h is going to the 0. Then as a result, I have the term which is e to the power of the x is completely independent of the h, because h is going to the 0, and I do not have anything inside this. It means that this term, it becomes like the coefficient, like an independent term with respect to the limit. Because you remember from the things that we talked about the limits law, we said that the limit of f of x, when x goes to any number, I call that x naught, and I have a constant term, which is c. Then when that thing happens is that what I'm going to do, I said that I have f of x, x is the variable which the limit is emphasized on. However, c is a constant, which means that it hasn't to do anything with the limit. Then we take this out, and we say that it's going to be the limit of f of x. X goes to the x naught, and I have c, constant, going outside. Do you remember this law from the laws of the limit? That we said that we take this one outside, the constant goes outside, because the limit is not emphasized on the x. Or I may have not said that because we didn't have so much emphasis on the limits when we just cut. And it's not part of too much of the IB program. Now, if you either have seen this before, or if you are learning it right now, Elliot, then you see that, okay, c is not part of the limit because it's constant. Then I take this outside. Now, when it comes to this, and also, just let me just give you one example for this. And you say that the limit, for example, of 4x to the power 2, when x goes to 2. Let's x goes to 2. Look at this. 4 is a constant. Then you say that, for example, you can write 4 times the limit of x squared, x goes to 3. Then now that's the time. You close your eyes. You lean back, substitute 3 there. It becomes 4 times 3 to the power 2, becomes 36. It's your option to take this one outside. You can still leave it there, then still you get the same answer. But if you just want to work with more fancy identities, that's one of the recipes. Otherwise, you can keep the C inside and do the limit. Now, any questions so far? Everyone is good? Everyone is feeling happy? Yes? Now, look at this one. I have the same problem. When h is going to the 0, I see that e to the power x is acts like a constant because h e to the power of the x has no term explicitly connect this one to the h. If it was e to the power h, I couldn't just look at it as a constant because h is going to 0. Then as a result, by using that identity, let me erase this part then. Shall I erase this part? I do not erase this one because I'm going to use it in 2 minutes. Now, if that's going to be the case, I take e to the power of the x outside, and I write this as the limit of e to the power of h minus 1 over h. H goes to 0. So far, so good? Now, I say, okay, what happens now? We have a limit. It's acting on the h. How to find the limit? How do you find the limit? You see, I close my eyes, I lean back, I do a direct substitution. If I put h equal to 0 today, how much do I get? You get e to the power 0 becomes how much? 1. 1 minus 1 becomes how much? 0. 0 over how much? 0. What do you have to do when I say 0 over 0? Huh? Scream and run. I love it that you still remember. Scream and run, because 0 over 0, that's what you have to run away from this. Then as a result, it means that you are not there. On the test, we had a similar case that you had to use, for example, the conjugate test. Now, what to do in order to resolve this issue? I'm just going to write it here on the top. In order to resolve this issue, I'm going to write it here. I say, whatever I see on the top, I rename it. Then I say e to the power h minus 1. I call it as what? Anything. I call it as tree, or house. I call it n. Let me write it with a different color. E to the power h minus 1, I call it as n. Then it means that this limit, when I'm going to, how much time do we have? We have half an hour, huh? The ring is 9:40. Yes, what? Now, we said that, okay, now if that's going to be the case, I'm still going to keep my e to the power of the x outside, which acts as a constant. Then I have the limit of e to the power of h minus 1. I called it, you can call it anything. I called it n. What is going to be the h now? If you call e to the power h minus 1 equals to n, how much is the h? Because I cannot leave h here. Yes. That's so true. Thank you. And in order to find the h, I say, okay, I have to find h from a term which is standing up there. The first thing which comes to me is that take minus 1 to the other side, then I get e to the power h equals n plus 1. Now, e to the power h is n plus 1. How much is the h? Let me write this down. Then h is you take ln from both sides. I hope everyone is okay with that from the advanced function course. Take the ln from both sides. Then you get h equals to ln of n plus 1. Please let me know if that expression makes sense to you from here today. Yes? Yes, yes, please. Does this make sense to everyone? Yes? Everyone is happy? Yes? Yes, Brooke? Can we take from here to there? Yes? I'm glad to hear. Yes?
I don't know, just,
From here to there, huh?
yeah.
But look at this. You have a to the power b equals c. You are interested to find b. You say, okay, I'm just going to look at inverse function. I take the logarithm from both sides. Then you see the log of a to the power b equals to log c. From the rules that we have on the first page, you see that if you have the power from here, it's like the hat. The weather is going to get windy, and the hat is going to fall off. Then you see that it comes down there. I learned like that. I said, this is a man, he is wearing a hat, it becomes windy, then the hat falls off. Then becomes, from here you get what? B times log of A. And it can be recovered, for example, the base at the end, equals to log C. Then from here you see, oh, B is equal to log C over log A. That's the spot. For here we took a shorter note. We said that from here we take the ln. ln is what? ln is the logarithm of anything which the base is e. It takes you to the ln. Then if you take ln from both sides, then you get the hat falls. Let me write it here. But you're okay so far with this. Now, from here, I'm going to write it there. I have e to the power h equals n plus 1. I'm going to take ln from both sides. What is ln? It's a logarithm with the base e. Then it means that logarithm with the base e, which I write ln, e to the power h equals ln n plus 1. And now look at the windy weather. The h falls off as a hat. H ln e equals ln n plus 1. And now, guys, look at this from one of the identities. From functions 11, you remember that the logarithm of anything at the same base, it has to be how much? 1. Thanks, Elliot. Then it means that ln from here, h ln e. ln e is how much? 1. Then you have h equals ln n plus 1. That's what I have written. Does it make sense now? Yes? Everyone is okay? Now. Okay, now. Then as a result, instead of writing h, I'm going to write this expression. ln n plus 1. I know that h is still going to 0. Now, I got another limit now. I talked for 2 minutes, then I give you 1 minute break. Then you see that. Now, I have another limit. The first thing that you may come to is that, okay, let's substitute it there to see how much do I get. If you do that, you say, oh my good Lord, look at this. What a mess is there. You want to do a direct substitution. It means that you close your eyes and take the value as h as equal to 0, plug it in there. But h goes to 0. Where is h? You do not see any h in there. Then you get a headache. You have to open your eyes and think for something to do. Now, h goes to 0. You have everything is written as n. You come back there. You see that if h goes to 0, how much is going to be the value of the n? If h goes to 0, can you think from there? H is going to be 0, then how much is going to be the n? Yes. 0? Why do you say that? That's right. Thank you. And look at this. We say that we know h goes to 0, and we come back to this change of variable. Oh, it has to be 0, sorry. The definition of the E is n to the power. I'm sorry, it should have been 0. Anyway, if you look at this, we see that if h goes to 0, and I put h goes to 0, it means e to the power of 0 becomes how much? 1. 1 minus 1 becomes 0, n becomes 0, which it means that instead of h, I write n goes to 0. Because of that change of variables, n now is going to 0. Now, things is weird now. Now I can close my eyes, stop to the 0 there. I get limit of 0, ln 0 plus 1 becomes 1, ln 1 becomes 0, then 0 over 0 again, you have to run away. Means that you are not there yet. Now, you are almost 2 minutes away from finishing this exercise. Now I say that you have to do a quick trick. I keep E of x there. And the thing which I'm going to do is that I'm going to use this thing which I learned before. And that was that thing. Then we said that if I have a over b, which is a fraction, still I have a over b, but I can also at the same time divide it to the same number where n is not equal to 0. You learned that before. For a ratio, you can divide both the numerator and denominator at the same number, or divide them by the same number, but that number should not be 0 to divide. If that's going to be the case, I'm going to do this. I love the music. Now, look at this one. I have n. Then what do? I divide all sides, both sides, by n. Then I have 1 over n times ln of n plus 1. I know that n is going to 0. You're almost there. Look at this. I haven't done anything except I divided both sides by n. I'm going to simplify that further. I'm going to write it here. Let me see if I'm still on. Yes, I'm on the screen. Now, I have e to the power x. Is it there? I have the limit. I keep the limit here. E to the power x as a constant times the limit. N divided by n. How much do you get? 1. Thank you. I get 1 over there. I have, what else do I have? I have 1 over n times the limit of something. Look at the rule of a windy day that you are walking on the street. You have a to the power n, n is your hat, the wind blows it up, and you get log of a. This is the same thing. Behind the log, you show there is a hat on the ground. You pick this up, you put it on your head. And now, what do you get? You get ln of n plus 1 to the power 1 over n. I didn't do anything. I was walking on the street. I noticed that there is a hat behind me. I pulled it up, put it in my head, and it comes over there. Now, whew. And I know that n goes to 0. I'm only one line from finishing it. then you get still e to the power of the x. It is here, and I have the limit. I take 1, and you know that when you have to find the limit, you have the root, you have the denominator, the limit expands to both of them. For example, you remember that you had the limit of 2x over x to the power 3. X goes to 2. It means that essentially you're plugging two limits. The limit of the numerator becomes 2 times 2 over the limit of the denominator. Right? Now I'm going to do the same thing. The limit of the numerator is 1. Then I take the limit of the denominator, which becomes the limit. I can keep ln outside as an operator, and I take the limit. That's a little bit tricky for this. ln n plus 1 to the power n goes to 0. This part is a little bit tricky that you have to make. You take the limit inside your limit. ln. That's a little bit thing that normally if you do this on the first time, you do not get that. Now you see it, you say, oh, I can do this now. Now, guys, look at this. Look at the definition of our good friend natural number. The limit of 1 plus n, 1 over n goes to 0. Anywhere you see this limit, do not calculate this. Close your eyes and say that's the natural number, Euler number, E. Look at this one. The limit of n plus 1 to the power of 1 over n goes to 0. You see, that's the same thing. Correct? Then it means that you have your constant e to the power x. You have 1. You have ln of what? The whole term as a limit of n plus 1 to the power of 1 over n, then n goes to 0 becomes how much? E, correct? The whole ln, the limit of n plus 1 to the power of 1 over n goes to 0, that's the definition of the natural number, which I wrote this on the board from the first minute of the class. Then as a result, you take everything, put as E. How much is ln E? 1. Because we know that the log of any number over the same base is 1. ln E is logarithm of E to the base 1 E. Then it becomes 1. Then you have e to the power x comes 1 over 1. 1 over 1 is how much? 1. I take 1. Oh my God, wait a minute. Oh my God, look at this. We started from here. Look at this. Such a beautiful, I think. Nobody raised this board for the next year until the next year. You have to keep it there. I have talked to the other teachers as well. Look at this. We started from here with some manipulations. Wow, we ended up there. We said what? We said the derivative of e of x, the rate of change of e to the power x, it worked. We saw, oh my God, we got to the same function. And isn't that beautiful? Isn't that, guys? You may wonder, I cannot see how beautiful is that. You can take 1 minute to stand up and have a great view if you want. And it becomes also stretched out. Oh my gosh. Ah, math is so beautiful.
So was that at 0 and then it showed up? I do feel like you recording all the process like that. It's like,
Oh, really? Then I have to charge you for that.
oh boy, not that.
I'm just kidding.
Oh, no, it's only us. Can I change my calendar?
Oh, really? Yeah.
Yeah, very hard. I'm gonna go read that. I'm gonna read that now. It's just done. I will. No,
To be honest, I didn't watch it again. There was one time I just forgot like a little bit. Sure, I
Also, but I charge you. Okay, guys, please everyone take a seat back.
You're welcome. Go.
Okay, guys.
I want to change my answer. It shoots up in the brain.
Eye contact with you when I read
Oh, that wasn't like stuff. I'm so excited to see those photos. There's a really good better one than the flowers. It's so nice. Just like scroll up. Oh, it's like what's the virus? I don't know how to do your book together.
But I don't know where to
Okay, guys, before we finish today, I just want to ask you before we move on. Yes. Absolutely. Guys, before we finish today, I think that's gonna be a good idea. Because the way that you are going to derive this all the things that because this one is becoming a very piece of important information for the whole calculus course, that you learn that the derivative of only one function in the whole universe, it's the function itself, and that's going to be e to the power of the x, then I believe that that's going to be a very good practice, that you know how to from there to get here. Then I just want to ask you, please, I'm not going to erase this. Spend how much time do we have? 10 minutes, huh? In these 10 minutes, please start on a blank piece of paper, you work on yourself to make sure that you start from here, and using the board, your notes, me, and your classmates, make sure that you follow each step to end up here. Within the next 10 minutes that we have. Look at me. You look, oh no. It's going to be very easy. Please make sure that you learn every single step. And also when you go back home, do make sure that you know how to work with it. Then the next session that we start, it's going to be when? And the day is coming. Tomorrow morning. Oh, then tomorrow morning, we are going to continue from there and work with so many interesting stuff. Then now, please help yourself. Look at it as a buffet. Help yourself and start working to start from there and die. And let me stop the recording.